In this video, we are going to be talking about nerve impulses, which specifically covers Chapter 7, Section 3. You should have watched the video on just the general anatomy of a neuron before watching this video. We're just going to talk about how electrical signals travel down the axon of a neuron. So due to the fact that we are basically regulating charged particles and their movement across the plasma membrane, this action potential actually can be measured in where we are showing that we can measure basically the kind of move through the cell. So what I want to point out again is that the inside at rest, so if we have our little cell here, remember the inside at rest will be negative, the outside will be positive. And in your neuron, if we kind of I'll draw kind of a not so great artistic rendering, but here's my dendrites with my cell body, my axon. If you were to actually say the axon of this nerve cell, you could actually measure the electric potential that exists inside the cell. At rest, because the inside of our cell is negative, we have a negative, what is called resting potential. So the potential is just basically a term for electrical conductivity. And in this case, we are at a negative potential. So we are at rest, the inside of our cell is relatively negative. However, if there is a voltage, and if that voltage is big enough, we will reach what is called threshold. So this threshold value, this dotted line that is going across our graph here, this represents the minimum amount of voltage change that the cell has to see in order to fire an action potential is larger, is at threshold or larger. So let's just say this is about minus 50 millivolts. As long as our voltage change is the same or larger than that number, that's when we're going to see this spike in our graph. And that spike, that represents that point in time where those sodium channels have opened. So those gates on those channels they've seen that voltage change, they've opened, and because of that, we're going to have positive charge flow into our cell until we reach kind of our maximum, which occurs at positive 30 millivolts. From here, notice that our action potential greatly drops. And this represents the period of time where finally those potassium channels have opened. Remember, they are hitting their snooze button. They don't want to get out of bed, but they finally are like, okay, fine, I'm up, I'm open. And so we see this sharp drop because now instead of having positive come into the cell, we have positive ions leaving the cell, leaving that neuron. And notice that we pretty quickly drop. This is in milliseconds, 1/1000th of a second. We pretty quickly drop back down to a negative charge. And we actually kind of overshoot that resting potential. We actually go a little bit too negative and then have to become a little bit more positive. This period here, that represents that time where the sodium-potassium pump is working to restore kind of our normal at-rest neuron. So every single action potential looks like this. We start at rest, we shoot up to positive 30 as soon as we hit threshold, and then we shoot back down to somewhere near rest again. And because every single nerve impulse looks like this, we often refer to this as the all or none phenomenon. Basically what this means is that if you hit threshold, if a cell gets to that threshold voltage change, you are going to get your maximum shift in voltage and you will then immediately fall back down. But if your voltage is below threshold, nothing will happen. So you're either going to fire or you are not. And you're going to fire to your maximum potential or you won't fire at all. And so that's something to keep in mind when we talk about action potentials. Also, due to the fact that this graph looks the same for every single neuron, there are different portions of this graph that are given specific names. For example, when we see that first key, this point in time of the cell is called depolarization. At rest, we have a polarization of charge in our cell, meaning that we have separated our charges. Remember, if two things are polarized, like our politics right now are very polarized, you're either on this side or the other side, there's no kind of agreement. When something is polarized, that just means that we've separated something. In this case, we've separated charges. We've put positive on the outside of the cell, negative on the inside of the cell. However, during an action potential, we are causing the inside of the cell to become more positive. So instead of polarizing our two sides of the cell, we are bringing them both kind of closer to equal charge. So we call this a depolarization because we are removing that polarization in the cell. Notice that after we hit kind of our action potential and we start to fall, this is when the cell is working to restore that positive negative charge difference across the cell. So we refer to that as repolarization. We have seen that we kind of overshoot and we kind of go too negative. We go past our -70 and we get a little over negative. That region is called hyperpolarization. And again, to get us back to at rest, to that kind of final resting potential, this is when the sodium-potassium pumps start working to restore us back to rest. So 3 key points in this graph. Depolarization, we're causing the inside of the cell to become much more positive. There's less of a charge difference across the membrane. Repolarization, we're trying to restore that charge difference. We overshoot what we needed to get to, so we become hyperpolarized. Remember, hypertonic, we have too much of something. And so we have to now have the sodium-potassium pump to get us kind of back to our resting potential. But that is an action potential. So this is how our nerves can send electrical impulses from one nerve to another or from one nerve to a muscle. We're literally just allowing for the diffusion of ions, and those ions are going to carry their charges across the plasma membrane, which is going to result in a signal being sent down our cell.